Welcome to Study Loop.
Capacitor being charged, and we want to know what is the magnitude of the magnetic field due to the current at the following radial distance from the wire. So we want to know for a distance of 1 millimeter. So the equation for the magnetic field for this capacitor is mu0 I r divided by 2 pi r squared, r being the distance from the center and r squared being the radius of the capacitor. And for this distance, we have 222 millitesla. Now for part B, we want to know at 3 millimeters, and this is outside the wire. So for outside the wire, the magnetic field is different. Is mu0 I divided by 2 pi r. And for r equals 3 millimeters, we have B is equal to 167 millitesla. And finally, C, we want to know at 2.2 centimeters outside. So we have for C is the same field as outside. So this is mu0 I divided by 2 pi r. Now r is equal to 2.2 centimeters. So B becomes 22.7 millitesla. For part D, want to know what is the magnitude of the magnetic field due to the induced current at the same distance as before. So for D, E, and E. So for D, the equation is the same thing as before, but with the displacement current divided by 2 pi r squared. R is equal to 1 millimeter. This gives a magnetic field of 1.25 millitesla. Now for E, this is outside. Now the field is mu0 I d r divided by 2 pi r squared. The field stays the same because it's from the displacement current. So this is inside the gap yet. So only the 2 centimeters will be outside the gap. So this gives us 3.75 millitesla. For R is equal to 3 millimeters. And for this was D, sorry, D, E, yeah. Now F is outside, so the field is mu0 ID divided by 2 pi R. And now R is 2.2 centimeters, and B becomes 22.7 millitesla. And G, we want to explain now why the fields at the smaller radius are so different, but the fields for the large radius are not. So we'll notice that this field is equal to this field here, but for the small radius, we have a big difference. And this difference occurs because the displacement current in the gap is spread over a larger cross-sectional area. Values of B within the area are relatively small. Outside the cross-sectional area, the two values of B are identical. So inside, they are different.